Okay, so what we're going to cover in the second half of today's lecture is estimating detectability of sources. So we talked about sensitivity curves and the different ways that we might want to represent signals, characteristic strains, amplitudes, and so on. What I'm going to go through in the rest of today's lecture is derivation of some simple scaling relations at leading order for in-spiral sources, and then also for backgrounds, and discuss some of the differences and what, again, the sorts of things you might see in papers. So I do have a section in the notes, gravitational waves on the back of an envelope. I think, given time constraints, I'm not going to go through this in any detail, but as I said, I'll make the slides available so you can look through it. What I summarise here is some recap of the electromagnetic radiation. I know most of you will have had courses on this in the past. If you start from Maxwell's equations and introduce the scalar and vector potentials, and you can combine them in a covariant form in which you have a single vector potential, the time component of which is the electric potential, and the spatial components of which are the vector potential for the magnetic field. You can reduce Maxwell's equations to this form. The derivative of F, this tensor, which is the antisymmetric differential of your vector potential, is the derivative of that, derivative of that is equal to mu naught times current. If you use this Lorentz gauge condition that the derivative of, so the divergence of the vector potential is zero, Maxwell's equations reduce to this form in a box, so that's the wave operator on the vector potential, is equal to mu naught times J. And that has this retarded Green's function solution that A is given by the integral of the current evaluated at retarded time, t minus the magnitude of x minus x dashed, divided by r times x dashed. So starting from this, you can then derive the leading order form of electromagnetic radiation by expanding the quantity of x minus x dashed here in the asymptotic regime, where mod x is much bigger than the size of the source region. So this means that x is everywhere much bigger than x dashed. And going through this procedure, you basically find that you have terms that look like this. Your field at large distances goes to 1 over r times an integral. The first term is the integral of the current. Then you have a time derivative of the current, second time derivative of the current, and so on. So I'm not going through this very carefully in the interests of time, but the slides will be available. You can check, and hopefully it's at least ringing some bells of previous courses you've done. But the point is that in electromagnetism, the first of these terms is a constant because it's of conservation of charge, but the second of these terms is not. This is essentially the time derivative of the dipole moment of the current distribution. And that tells you that at large distances, the radiative bit of the field is dominated by the dipole. So you have dipole radiation in electromagnetism coming from this time derivative of the moment of the current distribution. Now there's a paper by Bernard Schutz in the American Journal of Physics. This is kind of it's a sort of a public science journal in some sense. It's supposed to be things that high school kids can understand. He has this paper that derives some of the main features of gravitational radiation. What he says is on the back of an envelope. And doing this, you can get the essentially the form of the quadrupole formula for gravitational waves and the energy flux in gravitational waves. Straightforwardly, you don't get the right p-factors, you need to do full GR for that, but you get the right sorts of scalings. So the argument is basically that if you take Eric's equation, not really Eric's equation, so the Poisson equation for the gravitational field, del squared phi is 4 pi g rho. We know that that has this solution, again, it's from the Green's function, with the integral of rho over r. It's just superposition of the individual Coulomb potentials for each of the mass elements. So that's Newtonian gravity. If all you do to make gravity relativistic is include time delays, what we can do is, by this analogy with the vector potential, we can replace the integral of fixed time here with an integral over retarded time. So that's saying that the field at large distances responds to changes on the light curve. Okay. Now this is a solution to box of phi is 4 pi g rho rather than del squared phi is 4 pi g rho. This is not Einstein's equations. It's not too dissimilar to what you get if you do things properly in GR. But it's an analogy that is easier for people who've studied electromagnetism to understand. So if you now start with this retarded integral expression for the potential, and you do exactly the same thing you do in the electromagnetic case, you get a first term, which is the integral of rho in this case, and then you get a second term, which is the integral of the rate of change of density, which from the continuity equation, so d rho t is divergence of rho times v, you can relate to the total momentum in your source. Okay? And so in gravity, if you just do this simple retardation of time, what you get is that the field at large distances has a 1 over r bit, which is the usual mass monopole. Mass is conserved, and so this is constant. You then have the second term, which was the dipole moment, and is the dominant radiative piece in electromagnetism. This is also constant in gravity, and that's because momentum is conserved for gravitational interactions in a way that it is not for electromagnetic interactions. And so you conclude that the dominant time-dependent piece of a field is from the third term here, which is therefore the quadrupole term, and is the second derivative of the quadrupole. And so immediately you're led to this conclusion that at large distances, the oscillating part of your gravitational field depends on the second derivative of the quadrupole moment divided by distance. Okay, now this is the form you get in full GR. The factors you get here are on the right. You get slightly different things. I think Cliff will probably go through this in his lectures on Hamiltonian theory next week. But the point is, you can deduce that the way h scales is as I double dot over distance directly from this simple approach. You can also deduce that the energy carried in the gravitational waves should go like h dot squared, just by thinking about this potential as a scalar field that's carrying energy. Its flux is then the gradient of the field times the time derivative of the field, and those are basically the same at large distances. So you deduce that the energy carry is the derivative of the potential squared, and since the potential goes like I double dot over distance, the derivative of the potential goes like I triple dot over distance. Again, you don't get the right prefactor, you get a quarter of a fifth, but it's pretty close, and if all you care about is understanding the scaling and detectability of sources, then this is an easy way to get those leading order results. But you can't extend the analogy forever. Okay? So, sorry I went through that quite quickly. We don't have huge amounts of time, and you will do it more carefully in other lectures. But the point is, we've deduced that the amplitude of a gravitational wave goes like the second derivative of the quadrupole moment divided by distance. And the quadrupole moment is the integral of rho xi xj. And the energy carried by a gravitational wave goes like I triple dot squared, or d squared times h dot squared. So what we're going to do now is estimate these quantities for a Newtonian binary that is in spiraling, and we're going to deduce the form of the characteristic strain and so on for this type of source. Okay, so what do we need to do this? We need to work out what the quadrupole moment is. Now the quadrupole moment is rho times xi xj. It's the second moment of the mass distribution. We want to take time derivatives of it, time derivatives of position, of velocities. So the second derivative of the quadrupole moment is like the integral of rho v squared, but that's the energy density, so that's the kinetic energy, and from the Gair theorem, kinetic energy is the same order of magnitude as potential energy, and so you can estimate, and this will be useful for later in the lecture, we'll talk about supernovae. Roughly speaking, the I double dot is going to scale like the total mass times its internal Newtonian potential. Now the total mass is, so this is I double dot, H goes like I double dot divided by distance, and the mass divided by distance is the Newtonian potential of the source at the point where you're evaluating H. Okay? And so you have this scaling argument that the strain scales roughly like the Newtonian potential at the point where you're estimating the strain times the internal potential of the system. Okay? Now, we'll do the in-spiraling example slightly differently, but this is good to remember for other types of source where maybe you only know roughly what these potentials are like. Okay, so for a Newtonian binary system with masses m1 and m2, you've all done this at some point in the past. You know that the motion of these two objects is equivalent to the motion of a single object of mass mu. This is the reduced mass, which is the product of the masses divided by the total mass, moving in a fixed potential corresponding to an object of mass equal to the total mass. Okay, so you have this definition of mass ratio, reduced mass ratio, which is m1, m2 over m1 plus m2, and the distance of the two objects from the centre of mass is obviously given by R1 times M1 is equal to R2 M2, so the heavier object is closer to the centre of mass than the lighter one. Okay, so from this is one of Kepler's laws, you know that omega squared scales like m over r cubed. If you ever need to derive this, it's relatively straightforward. You remember that for motion in a circle, you have a central acceleration needed that's equal to v squared over r. That's equal to the gravitational force, which is gm over r squared. And you can also write this as r omega squared is gm over r squared. And so you deduce omega scales like m over r cubed. Now, the total energy in the system is the kinetic energy plus the potential energy. Kinetic energy, well, that's a half m1 v1 squared plus a half m2 v2 squared, but this equivalence to having only one object of reduced mass orbiting around in a fixed potential means you can actually get the kinetic energy slightly more easily. It's a half mu times, so it's half times this reduced mass times the velocity squared. And you also have a contribution for the gravitational potential, which is minus gm mu over r. Now, from this same equation, v squared is equal to gm over r. So you've got a half gm mu over r minus gm mu over r. So the total energy is just minus a half gm mu over r. Okay? So again, this is a result which you probably derived before. in most of my slides, I'm setting g to equal 1, so you can figure out where the g's have to go at the end. Right. So far, this is all just general properties of Newtonian orbits. We now want to work out what the amplitude of a gravitational wave is, and for that we need to work out what the quadrupole moment is. Okay? So the quadrupole moment, well, it's the integral of rho xi xj dv. You can, so that's either, so rho, we only have mass density at the locations of the two objects. So you can write this as either m1 times x1 squared plus m2 times x2 squared, or again, using this reduced mass analogy, you basically have a single object of mass mu that's orbiting at a distance r, which is the sum of r1 and r2. Okay? And so this quadrupole moment scales like mu times r squared. It has to have a time dependence. We need to take time derivatives of it. The way the time dependence comes from is the fact that it's a tensor, so and you have objects that are moving in circular orbits. So x and y, if you're in the plane of the binary, one is changing like cos of omega t, the other is changing like sine of omega t. So when you write out the components of this, you have something that looks a bit like cos squared omega t in your xx component. You have a cos omega t, sine omega t in the xy component. And then you have a sine squared omega t in the yy component. So again, if you do for GR, it's the trace-free version of the quadrupole moment that's relevant. When you subtract the trace, you're basically taking half of this sum from both of them. What you find is that having done that, you've got cos omega squared t minus sine omega squared t in these two components, and you've got cos omega t sine omega t in these two. So you have an h plus that is varying like cos 2 omega t, and an h cross that's going like sine of 2 omega t. So the first thing that tells you is that the gravitational waves come out at twice the orbital frequency, and in terms of the scaling here, we have I goes like mu r squared times cos 2 omega t, or e to the real part of e to the 2i omega t. Okay. So, yeah. We now want to put some more numbers back into this thing. From this relationship here, omega squared is m over r cubed. We can say that this r squared here is basically m over omega squared to the 2/3. And so we also have this cos 2 omega t here. So we have something that goes like mu, which is m1, m2 over total mass, times an m to the 2/3 times an omega to the minus 4/3, which is m1, m2 over m to the 1/3 times omega to the minus 4/3. Okay, so that's the scaling of the quadrupole moment. The scaling of h goes like h double dot over, I double dot over d, and so that second derivative brings down two factors of omega, so it goes from omega to the minus 4/3 to omega to the plus 2/3, and the mass factor remains the same. It's this m1, m2 over m to the 1/3. Okay, so we've now derived the form of the amplitude h, but in the various definitions we had in the first half of the lecture, we cared about things like characteristic strain. Now, characteristic strain also depends on F dot, so we need to know how the system is evolving, as well as the amplitude of the waves that are coming out. Okay? And so that's where we use the energy. We know how the energy relates to radius, and we also know how much energy is being carried away in gravitational waves. And so we relate the energy that's being lost from the orbit to this energy density in gravitational waves, and that allows us to compute the rate of change of frequency. Okay, so E dot, we said goes like, well, it goes like I triple dot squared, or D times H dot all squared. When you differentiate H again, that just gives you another factor of omega. So H dot goes like this function of mass times omega to the 5/3. E dot goes like that squared. And so you have an omega to the 10/3 scaling, and you still have this mu m to the 2/3 squared, which I've written there as m squared, so mu squared m to the 4/3. Okay. Now, E goes like 1 over r. Okay, so E scales like m mu over r. So E dot goes like m mu over r squared r dot. And we also know that r cubed scales like omega to the -2. And so mu over r squared, that 1 over r squared is a omega to the 4/3. And that r dot, I missed a factor of m then. Okay, that 1 over r squared. So 1 over r is omega squared over m to the 1/3. So that squared is omega to the 4/3 divided by m to the 2/3. And then r dot, well, you differentiate this, you have omega dot is equal to 1 over m over r to the 4th r dot. And so r dot is, running out of space, is omega dot times r to the 4th over m. So we'll do all this over here. Okay, so we have E dot is m over mu r squared r dot. We've just said that r dot is omega dot times r to the 4th. Okay, and so r dot over r squared is omega dot r squared, and r squared from this equation here, r goes like m over omega squared to the 1/3, r squared is m over omega squared to the 2/3, so you get an m to the 2/3 times an omega to the -1/3. Okay, so we had E dot was mu squared m to the 4/3 times omega to the 10/3. We now have omega dot is, well, putting this all together, we've got an omega to the -1/3 over here. We have an m to the 5/3 mu. And we now need to multiply this by E dot, which was mu squared m to the 4/3 times omega to the 10 over 3. Okay, so that was fairly involved, but what we've ended up with is the fact that omega dot goes like we have a mu over m to the 1/3. Something going on there.
So far, mu times m to the 2/3.
Let me consult my notes.
You're fine. You're fine.
So I thought I've now got mu over m to the 1/3, which is slightly different. I should have mu m to the 2/3.
No, you're fine. You have all sorts of powers, 5/3, and the powers in the chart.
Looking at this term here. So it's slightly
Oh, I
different.
see.
We'll just check. Okay. See if I can find it quickly, otherwise I'll move on. Dimensionally, I think it doesn't work out otherwise.
This is
Well, this expression is right dimensionally, so I must have used a factor of mu somewhere along the lines. Probably, well, almost certainly in this step. It was here. So the expression was omega squared scales like m over r cubed. And so you get omega dot scales like m over r to the 4th times r dot. And I missed this m in this expression here. So this m goes away. And so what you end up here is m to the 2/3 in the denominator, and so we have mu times m to the 2/3 times omega to the 11/3. Now you can write this term here, m1m2 over m1m2 to the 1/3, as mc to the 5/3. The reason, basically, is you've got dimensionally this has to be m s to the 5/3. And this mass combination is m1, m2 to the 3/5 divided by m1 plus m2 to the 1/5. This is the chirp mass. You'll hear lots of people talking about chirp masses. The reason it is important is because it is the thing that determines this leading order frequency evolution in a Newtonian binary. Okay, so we've now got all the results we need. We've got an expression for frequency derivative, we've got an expression for h, and so we can now write down the definitions of these various quantities that we introduced earlier, characteristic strain, and so on. Okay, so I'm just going to write up here the expressions we derived, and then we'll put them all together. Okay, so what we have is that the amplitude of a binary h scales like mu times n to the 2/3 times omega to the 2/3. So that's this expression here. Distance. And we have omega dot scales like mu m to the 2/3 times omega to the 11/3. And we also have E dot scaling like mu squared m to the 4/3 times omega to the 10/3. Okay. So we said before that the Fourier domain amplitude at a particular frequency scales like the amplitude divided by the square root of f dot. And so this must scale like, that's the 1/d factor from here, but we have a mu times m to the 2/3 times omega to the 2/3. And we need to divide by the square root of this quantity here. So square root of it, mu m to the 2/3 times, now we have omega to the 11/6. Okay. And so this is Chert mass to the 5/6 times f to the minus 7/6. Okay. So this is the first scaling. I've been using omega everywhere else. This is omega to the minus 7/6. Point is that the Fourier domain amplitude at a particular frequency scales like f to the minus 7/6 powers. And h tilde squared, which is that quantity you need for calculating SNR, goes like f to the minus 7/3. Okay. Now the characteristic strain we defined as h naught over root f dot, so this h tilde we've just calculated, times the square root of 2f squared. And so basically we're multiplying this quantity by omega, or f, and so that scales like f to the minus 1/6. So this is something you don't really come across that much. I mean, you may hear people talking about f to the minus 7/3 for h tilde squared. F to the minus 1/6 is rarely talked about, though if you know what characteristic strain, that's what you should see in the Newtonian regime. Okay, so we've dropped factors of g's and c's and things in various places. If you put them back in, you get expressions here, and also introduce the numerical factors. The details aren't important. The purpose of this was to work out how things scale with mass and with frequency. Okay, and we're, in particular, this one we'll come back to when we talk about backgrounds in a few minutes, because you have a different scaling for backgrounds, and the reason for that I will explain when we get there. Okay, so if you put in physical units, so we reintroduce all of the factors that we dropped, things scale like this. For a source at a distance of 1 megaparsec, radiating at a frequency of 100 hertz, and with masses basically the order of 1 cell mass, you have a strain of about a few times 10 to the minus 16. And now 1 parsec is very close. We don't expect to have in spirals that close to us, so we'll never see something order 10 to the minus 16, but you can scale it to other distances. The luminosity is order 10 to the 43 joules per second, again for a 1 cell mass binary close to merger. The number you will see people talk about for GW 150914 is much bigger than this, and that's because the masses are much higher. You have this scale about the square of the masses. So if you make the masses 30 rather than 1, suddenly you've got a factor of 900 squared here, so that boosts this up towards 10 to the 50. Okay, so if you think about the Earth moving around the Sun, that's producing gravitational waves. If we observe this at a distance of 1 parsec, we have a strain of 10 to the minus 28, and we're losing approximately radiating 10 watts of energy. It's not very much. It's not been spiraling particularly quickly. It's very likely anything will deduce the Earth is here because of gravitational waves. But that puts these sorts of things in some kind of perspective. Now, what we're interested in for an in-spiral is the maximum strain. Okay, and so we can't have arbitrarily large frequencies here. If we could build detectors at arbitrarily high frequencies, then we could get very high strains. In-spirals cut off when the binaries merge, and binaries merge when they get to a separation comparable to the ISCO of a black hole. So that's roughly 6m. And so if you replace if you work out what the frequency corresponding to 6 ELC squared is, that's about 1,000 hertz for a 1 + 1 solar mass binary. And if you set the frequency equal to 1,000 hertz, then at 1, this luminosity goes up to 10 to the 50%. So, as I said, you get a factor of 900 squared, so almost 10 to the 4, that's 10 to the 6. From the fact that the two masses in GW150914 were 30 solar masses, and then you get another factor of 10 to the 4 from the fact that the luminosity, so we observe the merger right at the most sensitive part of the detector, and we reach the conclusion that GW150914 was radiating a luminosity greater than the entire universe at the point of merger, but only for a fifth of a second. Okay, so now to make sources more reasonable, if we put this 1 + 1 solar mass binary on the parsec, h is 10 to the minus 21 at merger. The merger strain scales like m to the 2/3 because of the scaling of the merger frequency. Scales like order of mass. And so like it's in there, you find that you're left with a factor of mass to the 2/3. And so a million plus million solar mass binary would have the same strain at merger as a 1 + 1 solar mass binary if it was a factor of 10,000 further away. So at 10 gigaparsecs, a supermassive black hole binary with a million plus a million solar masses has the same strain as a 1 + 1 solar mass binary at 1 megaparsec. But the frequency is different. The frequency is 1 millihertz as opposed to 1,000 hertz. And so these sources we will see with space-based gravitational detectors, whereas the 1 + 1 we will see with something like LIGO. Okay, another source for space-based detectors are 1 + 1 solar mass binaries that have frequencies of 1 millihertz. These are not merging, they're very far from merging, but you can use the same formula that's even more valid because it's the Newtonian limit, and you find that at a distance of 1 gigaparsec, a millihertz compact binary has a strain of about 10 to the minus 23. Okay. And these are sources that we expect to be able to see with LISA as well. In fact, LISA is expected to detect thousands of millihertz binaries, and these are the typical strains of those sorts of sources. Okay, so I'm going to discuss a couple more things before we finish. First thing are eccentric binaries. A binary on an eccentric orbit, you can solve the Kepler problem with eccentricity as well. What you find then is that rather than having everything oscillating with a single frequency that's twice the orbital frequency, you get components at every integer multiple of the orbital frequency. And this was derived by Peters and Matthews back in the 60s. And you find that you can work out basically the energy flux carried by each of those different modes by working out the contribution to I triple dot squared from each one. The scaling with frequency is the same. You know, we have here E dot goes like mu squared to the 4/3 omega to the 10/3. That's the same, but it's now enhanced by a factor that depends on eccentricity and a particular multiple of the orbital frequency. The result depends on Bessel functions, the derivations if you want to. But if you have an eccentric orbit, you can't summarize things so neatly because you don't have emission at a single frequency at a single time. You have emission at all frequencies. And so what people tend to do in this case is to look at characteristic strains for each mode independently. Definition is the same. It's basically this one, characteristic strain is h naught over root f dot times root f squared, which is equivalent to e dot over f dot. And you basically find this characteristic strain is enhanced by a factor of root g over n. Just contradicting myself because there's an f minus 7/6 here and we've got an f minus 6 here. This is not I haven't got this factor, so sorry about that. So the slide is wrong. This is right. This is the characteristic strain is enhanced by this factor. It should be f to the minus 1/6 here. If you're working out h tilde for that particular component, it will be f to the minus 7/6. And again, it will just be multiplied by this root g upon n. So if you look in papers about
In the previous slide, f dot is multiplied by f, or is a function of f?
It's a function of f. So this is to indicate that this is f dot when the orbital frequency, so when the orbital frequency is frequency f. Okay. So clearly when the
But this
orbital...
is the, sorry.
Yeah.
This is the f of the Fourier transform or the orbital one, because it's not the same.
Right. So this is indicating that this is hc squared. So my notation is basically. This is the characteristic strain in frequency at frequency n times n. So the reason that this is n f dot is because here in the denominator is the rate of change of the frequency of that particular harmonic. And so this is the argumentation of f, basically. But so we need a unique, so at a given frequency, you will have, it may be easier to explain with this diagram. So you'll see these waterfall plots for people talking about eccentric orbits. These are showing this characteristic strain in a particular harmonic as a function of frequency. Okay, so these characteristic strains at each frequency are given by that formula I just showed. But clearly, there are points where the harmonics overlap, so they're all radiating at different frequencies. But they're radiating at that frequency at different times. Now, this E dot expression here is the flux when the dominant, so when the orbital frequency has value f. Okay, so this notation is indicating that we're working out a contribution at some other frequency when the orbital frequency has frequency f. The total hc squared you get in your strain spectrum is a superposition over all harmonics. But the contributions from the different harmonics are coming from different times. So if you add this all up, you'll get a slightly more complicated spectrum, which is what you need to get an SNR for an eccentric system. This is just a convenient way to represent things. Okay. So that notation I will correct before I give the slides. Barry posted somewhere. It was supposed to indicate that we're working out characteristic strain in harmonic n when the orbital frequency has a frequency f. That's not the same as saying what is the contribution of harmonic n at frequency. And obviously they're related to dividing by a factor of n. the notation is 4, so I will break that. Alright, so the last thing to talk about, well, no, we've got 2 more things to talk about, I don't know what the time is.
3 minutes.
Okay, that's fine. I want to talk about stochastic backgrounds, and I'm going to say a little bit about supernovae right at the end. Okay, so the definition we have of stochastic backgrounds, including this questionable positive density factor, was that omega is 8 pi g over 3 h squared d log f. And you can also relate this to the characteristic strain in the usual way, it's f squared times hc squared. Now, we can then ask, if we have an astrophysical population, how do we calculate omega for it? Okay. Omega is the energy density. And so, if you integrate omega d log f, then that should give us the total energy density in the background across all frequencies. Okay. So, from this definition, the total energy density is the integral of rho c squared. This is just this factor that I'm going to get rid of, times omega d log f. Okay. So, based on that, you can say, well, if I know that the gravitational wave background is being generated by a population, that population has some volume density, n of z as a function of redshift. This coding should be code moving. Right? Then the total energy density in the background today can be written as an integral over this, let's see, of the energy produced by each one of those sources. Okay. So what we want to do is integrate the energy over all frequencies. So that is the integral of d df df. We put in this factors of f and 1 over f, so that this becomes d log f. But essentially what we're saying here is that we integrate over all frequencies d df, that gives us the total energy, and then we integrate that over redshift to get the total contribution from all sources at all redshifts. Now there's this factor of 1 plus 1 over 1 plus z here, that is redshifting of energy. So as the universe gets expanded, the wavelengths get stretched, the energy density decreases. Okay? So this 1 over 1 plus z factor is accounting for the fact that what we're calculating here is the intrinsic, it's the energy density at the time the source was generated, gets redshifted by the expansion of the universe, and so the observed energy density today is slightly different. Also, the observed frequency today is also slightly different, and so you have to account for that too. Okay, so from this relationship between the spectral density and the total energy, you change the order of the integration here, and you deduce that omega must just be equal to the integral of n over 1 to c times f df. Okay, this has to be evaluated at the emission frequency, not the observed frequency. So we've got the energy density at frequency f. For a source at redshift z, the emission frequency was f times 1 z. Because the emission frequency was higher because it's being redshifted to this point. So if you have a particular population model that gives you n of z, you can work out f df for your systems, and then you can construct this integral. You can get this energy density in sources today. This is a paper that only exists in the archive by Sterling Finney. It's called A Practical Theorem of Gravitational Wave Backgrounds. It's a very useful paper that many people have cited, but it was never published because still, having solved the problem was not sufficiently motivated to actually publish it in a journal. Okay. So what does it mean for particular backgrounds that we might care about? Well, let's suppose, again, spell checker, inspiring binaries. Inspiraling binaries. Okay, so we've got inspirals. We can use these results we derived here to work out what this FDDF scale is. Okay. So DDF is ddt divided by dfdt. We've got expressions for both of those. We have E dot here, and we have omega dot here. So we can deduce that FDDF. Well, you get one factor of f here, you get omega or f to the 10 thirds here, so that gives you omega to the 13 thirds. You then divide by omega to the 11 thirds, and so you're left with an f to the 2 thirds. And then the mass factors, you take this divided by that, and you cancel one lot of mu times n to the 2 thirds. So you're left with mu m to the 2 thirds, which is this Chert mass to the 5 thirds. And so the energy density in the background is the integral of this and the redshift. You need to evaluate this for the redshifted frequency, which is today's frequency times 1 plus z, and that changes this factor of 1 over 1 plus z to a factor of 1 over 1 plus z to the 1/3. This is then just constant. It depends on the distribution of sources over redshift, which maybe you know, maybe you don't. But in terms of what's present in your detector, you have this omega background that's getting like n to the 5 thirds times f to the 2 thirds. Okay. Now the characteristic strain was related to omega by this expression omega is f squared, I guess proportional to f squared hc squared. And so hc goes like the square root of omega divided by f. And that gives you f to the minus 2 thirds. Okay. And then the energy density in the background, so the spectral density of the background, which is omega over f cubed, gives you f to the minus 7 thirds. Okay. Now, you'll notice that we've got a characteristic strain here that scales like f to the minus 2 thirds for a background of inspiraling binaries. And yet for an individual inspiraling binary, we have f to the minus 1/6. Okay? So these are different. And they're different by a factor of the square root of f. So why is that? Well, the reason is because of match filtering. Okay? This definition of characteristic strain for an inspiraling binary was assuming that we were doing match filtering. So we have a template and we're using that to dig the signal out of the data. When you're doing that, you enhance the signal by this factor of the square root of the number of cycles that you spend in the vicinity of a particular frequency. Okay? Now, if you have a source that's inspiraling over frequency, and it spends a particular time t in a given frequency band, then the number of cycles it produces is just f times time. Okay, and so you enhance the signal by this factor of f times t. Now, for a background, we're not assuming we're doing any match filtering. We're just looking at the energy density in the background, so we don't get this enhancement from the number of cycles, but we do get an enhancement from the number of sources. Okay, so you have this background that's been generated by a superposition of sources. The energy density in a given frequency bin depends on the number of sources in that frequency bin. And that, it depends on how long it takes the source to pass through the frequency bin. We've specified this n of z. This n of z is the rate at which sources are merging, say. That's something we don't know, we may or may not know, it's just a constant. But if sources are merging at a particular rate, then the time they spend in each frequency band is just that rate times the length of time they're in the frequency band. So the number of sources contributing to your background itself scales like this same time, which is the time it takes the inspiral to pass through that frequency range. And so you enhance your energy density by time, and that's the square of hc. So your background gets enhanced by t, but your inspiraling sources, because you're doing match filtering, get enhanced by f times time. So that ratio is then gives you this square root of f difference between the two. Okay. So this is something that people often ask questions about. Why are backgrounds f to the minus 2/3, whereas individual sources are f to the minus 1/6? And that's because you're talking about different things. There is an embedded assumption here about how we're digging sources out of the data, which is present for inspiraling sources because of match filtering, but not when we're representing backgrounds. So if you look in papers, you'll typically see people will do simulations, they'll calculate these energy densities for their population, and they typically see, so this line, this straight line that's drawn here is an f to the minus 2/3 line. In this particular case, the simulation agrees very well with the frequencies, not so much at high frequencies, and that's basically because of what people call popcorn noise. Essentially, when you get to these higher frequencies, the number of sources per bin is of order 1, and so Poisson fluctuations, again, it's not error fluctuations, but the Poisson fluctuations, the uncertainty in, so the variance of a Poisson distribution is the square root of the mean. So if your mean is 1, then you have plus or minus 1 plus or minus 1 events in each bin. So some of these have no sources, some do, so that's why we start to deviate from the f to the minus 2/3. We are assuming that we have a continuum of sources contributing to get this f to the minus 2/3, and so that works at lower frequencies, but not at higher frequencies. Okay. So inspiring sources and backgrounds, they're probably the most important things to be able to understand these sorts of scalings for. But if you want to do it for other types of source, you can estimate strains for supernova here for continuous wave sources. For a supernova, you might expect to get gravitational waves if the supernova is asymmetric. So in order to get gravitational waves, we need this time-changing quadrupole moment. That doesn't happen in spherical symmetry, but if you have something, processes that break that, you can produce gravitational waves. If you want to work out roughly what the strain might scale like, you can use this very old theorem expression I wrote up. I had on one of the earlier slides that H scales like the Newtonian potential times the internal potential. So for a supernova, this is typically something like a neutron. The star has a very dense core when it collapses. So the Newtonian potential is pretty close to that of a neutron star, which is highly relativistic. So this internal potential can be order of point of view. So in this case, say 0.2. And so what you get for this estimate of the strain you could get from a supernova, you take this internal potential, multiply it by the Newtonian potential, which is basically Gm over the distance to the source. And if you assume you have a one cell mass star at a distance of 10 megaparsecs with this kind of internal potential, then the maximum strain you could get would be order of 10 to the minus 21 at that distance of 10 megaparsecs. Okay, so 10 to the minus 21, this is quite detectable by LIGO. 10 megaparsecs is the distance to the Virgo cluster, so that volume is sufficiently large that you might expect a supernova every month or every few months. LIGO has not seen gravitational waves from supernova so far. That's because this is really an upper limit on the strain. It's assuming all of this potential radiated gravitational waves. Simulations of supernova typically have several orders of magnitude lower asymmetries than you get from this LIGO calculation. So strains at Virgo are more like 23 or 24, so it's unlikely we will detect a supernova unless it's in the local universe, meaning the Milky Way or one of the Magellanic planets. Now we are overdue a supernova. That's only one for 100 years or so, and that's the typical rate, is one every 100 years, and Milky Way type run. So there's some optimism that one might happen over the timescale of advanced LIGO. So the other type of source that I'll talk a bit more about tomorrow are neutron stars. So a neutron star is not a black hole, so it can have a quadrupole moment. As Eric said this morning. So if you have a neutron star that's deformed in some way, this could be an internal deformation due to fluid processes, then its quadrupole moment, because it rotates rapidly, is changing, and that produces gravitational radiation. So if you can approximate this very crudely by saying that a quadrupole deformation is a lump of mass that's bolted to the side of your neutron star. And so it's the quadrupole moment that contributes is delta m times the radius of the neutron star squared, and so that gives you the scaling for the sorts of amplitudes you might get. Okay, and so if you take mass of neutron star has radius of neutron star squared, so mass of neutron stars is about 1 solar mass, radius is typically 10 kilometers, and you assume a frequency of 1 kilohertz, and you take a derivative of this, you find that h for a neutron star scales like this times 10⁻20 at a distance of 1 kiloparsec. So a kiloparsec is a typical distance to a neutron star in the Milky Way. So if epsilon was significant, we should certainly see these things with gravitational waves. But in the lecture tomorrow morning, I'll give some recent results from LIGO on strings from neutron stars. We're already placing limits that are more like 10⁻24, 25 on galactic neutron stars. That's because you really can't have a perturbation on the surface of a neutron star that's that big, because the surface gravity is so great. And so the epsilons that models suggest could be supported are more like 10⁻⁷, 10⁻⁸, which makes this amplitude much, much smaller. And so that's the reason we haven't seen any so far. Okay, so that's everything I'll say today, other than to advertise this tool that some of my former PhD students put together. It's at this website, and it shows sensitivity curves of the various types that I was talking about today. So if you go to this app, you can select what you show. So we talked about these various ways in which you can represent sensitivity. There was the power spectral density, which is this Sn of f. There was the string density, which was f times Sn of f. And then there was the energy spectral density, which was this f cubed times Sn of f. You can select which of these types of sensitivity curve you want to see. You can choose a bunch of different detectors that you might want to include or not, and different types of source. It's been updated to include things like the first gravitational wave detection. So first of all, what is being plotted here is the thing you need to calculate this SNR squared by integrated by I. So this is the characteristic strain plot. So we're plotting f times sh here, and then this curve represents f squared times h tilde squared for GW 150914. Okay. Now you'll see that if you change to power spectral density, the curves become a bit steeper at low frequency. That's because going from characteristic strain to power spectral density, you're removing this factor of f. So you're increasing the quantities at low frequency. If you go to energy spectral density, you now multiply by a factor of f cubed, and so you bring down things at low frequency. And so the energy spectral density makes pulsar timing detectors look very good relative to the others. This is purely because we multiply by f cubed, and these things are at less frequency. So you gain factors of 10 to various powers. And so this is a useful tool for presentations and talks. When people want to, it's always nice in an introduction to a talk to say, well, if we have all these gravitational detectors and they operate in these different frequency bands and they see these different types of source, and this is a useful tool to do that. So anyway, that's all for today. Tomorrow morning I will talk a bit about gravitational wave sources and the astrophysics of gravitational wave sources, and then in the afternoon I'll cover some topics on data analysis.